Good morning, everyone. So now in today's session on high-speed aerodynamics, we will discuss about what is acoustic speed and Mach number. Okay. So coming to what is acoustic speed, how the particular derivation has been come, we will be seeing in this one. So what we will be doing is that we will be considering an acoustic wave moving in a stationary fluid with a speed of a. So we are considering the acoustic wave. So there is a wave which is moving in a stationary fluid. So in a stationary fluid, acoustic wave is moving with a speed of a. Okay. So properties of a fluid changes due to the presence of the acoustic wave. So whatever the fluid properties will be there, since that acoustic wave is presenting, it is going to change their properties. So these property variation can be predicted using the one-dimensional conservation equation. So whatever the properties changes which are going to come, so what we are doing, we will be predicting them using the one-dimensional conservation equation. So for simplicity, what we will going to do is like assume the acoustic wave to be stationary. So we are assuming that acoustic wave is stationary and the fluid to be passing across the wave with a velocity of a. So we are telling that whatever the acoustic wave is there, so this is stationary, we are telling. So, and we are telling the fluid will be passing through it. So whatever the fluid will be there, it is passing through it at a velocity of a. Okay. So as we are telling here also, acoustic wave moving in a stationary fluid with speed we are telling. But here we are considering the acoustic wave to be stationary and fluid is passing through it. As for simplicity purpose, we are going to consider this thing. Okay. So now what we are going to do is like we will be considering a control volume. So we are taking one control volume. So for understanding, central hatched portion can be exaggerated as a acoustic wave. So in middle one, we are going to exaggerate as a acoustic wave. We are telling. So let pressure, density and A, let P, rho and A are the pressure, density and velocity ahead of the shock. So acoustic wave, P, rho and A. So these three are nothing but pressure, density and speed. Okay. So acoustic wave being a small amplitude disturbance induces small change properties while fluid is passing through it. So whatever the acoustic wave which we are telling, it is nothing but a small disturbance generally. So when a acoustic wave is nothing but what we will be telling is like when fluid is passing through a medium, so there will be a disturbance. So that one we will be calling it as an acoustic wave. So now what we can do is like those changing in the properties which is going now. For example, we can tell it like we can say like acoustic wave means like when there is an sounds which we will be hearing from the when vehicles are passing through, right? So that is nothing but when the horn is honking, so the whatever that medium which is passing through that fluid will be creating that disturbance. So means vibration will be created inside that medium of the air. So which we are going to when we are hearing it one, so those are nothing but a sound waves will be called. So those technically which we will be going to call them as a acoustic wave. Okay. So this acoustic wave is nothing but a small amplitude of disturbance which we are considering here. So that induces the change in properties while passing through it. So what we are telling, acoustic wave is stationary and fluid move passing through it, right? So when the fluid is passing through this particular one, so this small disturbance, so there will be a smaller change in the properties will be there. So hence behind that one, so what is that smaller change is nothing but P plus dP, rho plus d rho and A plus dA. So these three are nothing but the pressure, density and velocity changes behind the shock wave. So ahead of the shock wave, general we are having of the P rho A will be there. Behind the shock wave, we will be having the change of it. So we can consider like that. So this is nothing but a shock acoustic wave. So this acoustic wave which we are going to take it. So ahead of this one we are having these properties and behind this one due to the small disturbance which are considering to be there for this acoustic wave. So because of that one, these properties are going to change. So that's what we stated right here. Acoustic being wave being amplitude smaller amplitude disturbance that induces the small change in the properties when it is passing through it. So when the fluid is passing through it, so there will be small changes in the properties will be there. So that extra small change is going to add to our main one. So in this one, what we will going to see is like how it will be coming application of the mass conservation and momentum conservation we will be taking at the inlet and exit of the control volume, which we have seen is. So what is the continuity equation we know? So rho A, right, equal to constant. So this one we can write it as, so d rho A means it is inlet. So outlet what we are telling, rho plus d rho, and A what we are telling, A plus d rho. So this is the inlet, this is outlet. So now samely, if we are considering the momentum equation, what we are having, P rho A square equal to at inlet. So at exit what we will be having, P plus dP into, plus rho plus d rho into A plus dA whole square. So these two are the continuity equation and momentum equation, right? So now what we will be considering, we will solve for the continuity equation. So what is that continuity equation we are having? So rho into rho A equal to rho plus d rho into A plus d rho. So now when you solve this particular one, what we will be having, rho A plus rho into d rho, this is dA, okay. This is dA. So what we will be having, these two, then these two, and these two. So rho A, rho into dA plus A into d rho plus d rho into d. So now what we are going to take, this dA into d rho will be neglected because of small quantity. So now what we will be having, rho A equal to rho A plus rho into dA plus A into d rho. So rho A will get cancelled out, right? So now what is the equation is there? From here we can write rho into dA plus A into d rho equal to 0. So from there we will write for A equal to what is minus rho dA. So d. So A from here A you can write minus rho into dA by d rho. So this is the what we are telling. A is nothing but a velocity, right, which we are considering. So A equal to minus rho into dA by d rho is the expression which we got from the continuity equation, right? Similarly, what is the momentum equation? We have P plus rho into A square set inlet. So at exit it is P plus dP into rho plus rho plus d rho into A plus dA whole square, right? So now what we are going to do, we are going to expand this one. So P plus rho A square into, so P plus dP will be same, then rho plus d rho into, so what we can write, A square plus 2A dA plus dA square, right? So now what we can write, dA square is smaller one, we can neglect dA square. So now what we will be having, P will be getting cancelled out both the sides. So rho A square equal to dP plus, so now what we are going to do is, we multiply this entire term with first one, then this entire with the second one. Okay, so now what will be there? Rho into A square plus rho into rho A dA plus what we have? dA square anyhow it is neglected, right? So only, sorry, let me just remove it. So since this is neglected, what will be the next equation? let's not get confused. So rho A square equal to dP plus rho plus d rho into A square plus 2A dA. So this is the expression, right? So now rho A square equal to dP plus rho A square plus 2 rho A dA plus A square d rho plus 2A dA d rho. So now what we are going to do is like dA d rho, since it is very smaller one, we are going to neglect it. So neglect. So here also this is neglected. So now from here what we can write? So both the sides we are having rho A square will be getting cancelled out, right? So now further how we are going to? So dP equal to, then write minus 2 rho A dA minus A square into d. So this is the expression which we got. Now this particular one, what we are going to do? So what we got here, dP equal to minus 2 A dP equal to minus 2A rho dA plus minus A square d rho. So this is the expression, right? This is what we got, A square d rho. So now from here we are going to find for the dA. So what is the dA? So dA we can write it as, so let's dP plus A square by d rho will be same. So dA we can write it directly minus 2A into rho, right? So this is the expression which we got. So now what we are going to do is, so what we got from the continuity equation, A equal to minus rho into dA by d rho, right? So from here what we got, we know A equal to minus rho into dA by d rho. So this is we got from the continuity equation. Now what we are going to do, we got the dA value, right? We are going to substitute inside this expression. So now what it will be there? So A equal to minus rho. So we will substitute. So this will become dP by d rho. So plus A square only will be there minus 2A rho, right? So what will be there? Rho get cancelled out. These two will be cancelled out. So what we will be having? 2A square equal to dP by d rho plus A square. So further we can write it as A square equal to dP by d rho plus A equal to under root of dP by d rho. So this is the general formula for acoustic speed or speed of the sound form, right? Now further we are going to see how it is going to change in the isentropic relation, how it will become. So now for that one what we will be seeing is like, we will see the physical process occurring for this sound wave or acoustic wave. So first, whatever the changes within the wave we will be considering at a slide, that is flow gradients, whatever it will be there, they are small. Since we are considering here the changes within the wave is slight, so we are taking the gradients are also small. So this implies that it is irreversible. Dissipative effects of friction and thermal conduction are the negligible. Moreover, no heat addition to the flow inside the wave will not be considered. So hence, the process inside the shock wave must be isentropic. Since we are considering it is irreversible, dissipative effect of friction and thermal conduction are negligible, and no heat addition. So it is isentropic condition. So the rate of change of the pressure with respect to the density, what we got from the previous expression, that we can write it as a, since there is a whatever the process inside the sound wave is isentropic condition, we can write dou P by dou rho S. So with isentropic condition change. Now what we know, the speed of sound is direct measure of the compressibility of a gas. So we know that rho equal to 1 by V. So from here, so d rho will be minus dV by V expression. So what we are telling, a square, we can write it as dou p by dou rho of s in terms of minus of dou p by, we can write dou p into v square, right? Now further we can write it this one as, so what we can write v by 1 by v, so that v square will be coming, and this one we can write dou v by dou p of s we can write. So now this expression a square. So now what is there? A square equal to, so tau means this entire expression is nothing but tau s. So v by tau, right? So this a we can write by v by isentropic compressibility, that is tau. So that is nothing but 1 by v into dou v by dou vs of isentropic condition. So this is one condition for the PM which we will be getting. Now for calorific perfect gas, what we know, isentropic relation is PV power gamma equal to C, right? So where C is constant. So what we are going to do is like we are going to differentiate, and we know the expression for V equal to 1 by rho condition. Now for this particular one, what we can write, P into 1 by rho over gamma equal to constant, we can write, right? So further this particular one, what we are going to do, we are going to differentiate. So when you differentiate this one, what we will be write, dv by d rho of P by rho gamma equal to d by d rho of C. So this is anyhow, it will be 0. So this side term we will be taking from the coefficient rule. So that will be like, what we will be having, rho gamma into dp by d rho minus P into gamma into rho gamma minus 1 divided by rho gamma square. So rho gamma, so this is nothing but what it is there, d by dx of f of x by g of x. What we will be writing, f dash of, sorry, so what we can write this one, d by dx of f of x by g of x is nothing but f of x into g of x minus f of x into g dash of x divided by g of x whole square, right? So now same condition, if you are taking that one, so what it is there, rho gamma, so it is constant. So for P, dp by d rho, okay. So minus of P is constant. So for rho gamma, we are differentiating. So for that one, gamma into gamma, rho gamma minus 1 divided by, so g of x square. G of x is nothing but for rho gamma. So whole square is rho gamma square power 2. So now from here, what we can do, if we are equating it to 0, right? Because d by d rho of C equal to 0. So now from here, what we can write, rho gamma dp by d rho minus p rho gamma minus 1 equal to 0. So from here, what we can write for the rho gamma dou p by dou rho of condition equal to P into gamma rho gamma into 1 by rho we can write, right? So for this one, what we can do, rho gamma will get cancelled out. So what it will be there, dou p by dou rho of s equal to gamma p by rho, right? So what we know, a equal to under root of dou p by dou s. What we are going to do here, a equal to under root of gamma p by rho, right? So what we know further? P equal to rho. P by rho equal to R. So then A equal to under root of gamma R. Right? So that is the expression. So what we will be getting? A equal to under root of gamma RT. So this is the general relation for the speed of sound for a perfect gas. So most of our condition, what we are going to take is of this one. So because we are considering the relation of the perfect gas. So for that particular purpose, in problems if you are getting means A equal to under root of gamma RT only we will be substituting. So we already know gamma equal to 1.4. So it is 287 and temperature is a particular location, what atmospheric condition temperature what we are having of the 287 which we are going to substitute. So this is the expression for what we got for the speed of sound, right? Now from there what we know further, what we are going to see like how the Mach number relation has been. So generally what we know is Mach number is nothing but speed of sound, speed of object to the speed of sound. So this particular one, free stream if you are considering means how we will be rating Mach number free stream equal to velocity of the free stream. Okay. To the speed of sound at free stream condition. Uniform free stream condition, velocity of the object at free stream condition, what is that? So these two will be given. So for that what we will be taking is like how it has. So we will be taking the flow is uniform with a free stream velocity of V infinity, the streamline curve in the flow field where tangents of the local velocity at every point along the curve. So streamlining is nothing but it is a curve in a flow field whose tangent to the local velocity, which is tangent to the local velocity vector v at every point along the curve. So like this it should be. So what we are doing, considering an arbitrary point in the fluid. So what we are going to do? So this point we are considering. So this will be having the properties like pressure, density, velocity, temperature. We will be having. So what will be then? So this is inside a flow field, right? So whatever the flow quantities at this particular point 1, which is there. So at particular point 2, if it comes means it is going to change. So from one point to another point, it will be going to vary. So for that particular one, what we are going to take is like A, we are going to take it as speed of sound for the uniform free stream. So from there, so Mach number free stream Mach number is nothing but the velocity of the object to the velocity of the sound. So that is nothing but A infinity. So this one will give us a Mach number relation. So now, so how this particular external aerodynamics for flow, how that has been divided. So category of flow for external aerodynamics. So Mach number is less than 0.3. So that one will be considering it as incompressible flow, and we have seen also at this particular time the density changes, whatever it will be there, it is negligible. Okay, so it's no, we are not telling it is not there, so it will be there, but it's negligible. Change in density is negligible. So now next condition, what we are, if it is m is less than 0.3, it is incompressible flow. So if it is 0.3 to Mach number is 0.8 means it is subsonic flow condition. So where we will be seeing the density changes significant, but we will not have any shock wave appearance. Okay. So now further 0.8 to Mach 1 point. So it is a transonic regime we will be calling. So inside this one, we will be having a shock wave appearance will be there, and for inside a body, there will be a region divided between the subsonic and supersonic region will be dividing the flow will be happen. So this transonic flow will be characterized by the mixed region of locally subsonic and supersonic, because we have the range, it is between 0.8 to 1.2. So that's why we have the mixture of both subsonic as well as the supersonic flow will be there for the transonic conditions, right? So next is we have the Mach number between 1.2 to 5. So we will be calling it as a supersonic flow. So they were everywhere in the flow is acoustic speed. So what we have seen here as before equal to under root of gamma RT, right? So this particular one value will be, entire flow will be above than this. So that is why, right? So what we are telling, M equal to P by A, right? So if A and V are same, means we will be having a 1. So what do we have? If P is above than A, then M will be more, right? So when above more, then what will it means? Entire flow field, it is more than the acoustic speed or the sound speed of sound. So what that location, what will be happening? So there will be a observe shock waves appearance will be coming, and across the shock waves, the streamline changes the direction. Whatever the streamlines will be there, it is going to change across the shock wave, right? So next is Mach number, greater than 5. Here this is greater than. So if it is greater than 5, so what we will be having, we will be calling it as a hypersonic flow, where the temperature, pressure, density of the flow increases almost explosively across the shock wave. So there will be abrupt changes in the pressure, temperature and density values will be there across the shock wave. So beyond that particular shock wave, what we will be calling it as a hypervelocity flow. So this is how the Mach number flow regimes will be there. So between less than 0.3, we will be calling it as incompressible flow, where d rho is negligible. So in subsonic flow, 0.3 to 1.2. So in this region, we will be having the 0.2 to 0.8. So this is subsonic flow condition, where the density effects will be considering. So then we have 0.8 to 1.2, where we have the appearance of shock wave will be there, and it will be locally subsonic flow as well as the supersonic flow regime we are going to observe in a flow field. Okay, so next 1.2 to 5, we will be calling it as a supersonic flow, where we are going to see the formation of the shock waves will be there, and the streamline direction is going to change entirely behind the shock wave. So then 5 to 10 is, we will be calling it as a hypersonic flow. Like above 5, we will be calling it as a hypersonic flow. So where we will be having the flow properties going to change entirely across the shock wave. So beyond that Mach 5, we will be calling it as a hypervelocity flow. So this is all about what is the acoustic speed, the formula how we got from the from the continuity equation as well as the momentum equation. We got the relation for the A value, that is speed or acoustic speed or speed of sound value. Then from there we have seen what we know, the formula of M equal to Mach number equal to velocity of the object by the speed of sound. Then from there we have seen the different flow regimes for the external aerodynamics, how the condition will be there, and this is the flow field for the Mach number variation, how the flow regimes are going to change. Okay, so this is all about the acoustic speed and the Mach number for this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.